That's a very useful result of the internal model principle, that you can easily find the type of system by just counting the number of integrators in the forward path. But remember that these are the assumptions if you want to use this simple rule. If I want to give you another example, and the question is, what is type? And this is the question we have, this is the example we have. We have this system, reference, output, and the question is, what is type? Okay, this example is not in this format because it doesn't have the unity feedback. So because of that, you cannot easily find this rule. But if you somehow, if you can write this block diagram or redraw the block diagram in that format such that it gives you the same transfer function from R to Y, but it has also a unity feedback. How I can do that? Because it is a simple example, I can write it in this format. Basically, the transfer function from R to Y in this example is 1 over S plus 1, which means that these two block diagrams are equivalent. Because this one is 1 over S divided by 1 plus 1 over S, which is actually 1 over S plus 1. So, and when you have it in this format, because the forward path has one integrator, therefore type is 1. So from this representation, you can say that type is 1. But from that representation, if you want to find the type, you should go and check the definition of the type, see if the steady state error is 0 to step and is not 0 to ramp, which is actually the case, but you should do all those calculations. So another way to do that, you should find a way to write the transfer function in this format, which is actually not difficult. I will ask you in an exercise to do that, to find a way to draw a block diagram with unity feedback when you have the closed loop transfer function. But it is not actually difficult, it's just some simple calculations. Okay, that was the first part of the theorem. The second part of the theorem, we are talking about internal model principle. The first part was about having disturbance equals 0 and we have the reference. And the second part is actually the opposite. When we have, let me redraw the block diagram because we are going to talk about the other case as well. So we have G of S, Y of S here, disturbance, controller, and reference here. So the second part of the theorem says that if, again, as I said, the stability is one of the assumptions and also the unity feedback. But anyway, if the second part says that if R of S is 0 and D of S is in the form of 1 over S to power n, which means that if D of S is 1 over S, it means that you have a disturbance which is a step. And what this step means, it means that, for example, the example I gave you about the frequency in the power grid, I said that it could be that one big factory switches off or switches on. So it means that you have a constant disturbance because it just switches off and on. In that case, we have D of S is equal to 1 over S. But in general, if D of S is 1 over S to power n, according to the theorem, DSS is 0 what it means. I will explain why, but let me write the theorem. The permanent, or the effect of disturbance on permanent or steady state output is 0 if and only if K of S has the unstable poles of D of S. I can give you a simple example here. We have this control loop, reference is 0, and we have disturbance, and the transfer function of the plant is 10 over S plus 1. And in this case, if actually it's also easy to find the response to disturbance and to do the calculation on paper, but we can show that reference is 0 and output is 0, and at some point if you apply disturbance, let's say if you apply disturbance here, if this is d of t, and I'm trying to plot y of t as well, so y of t before that is 0, after that if you have that, it would be something like that, and this value is almost 0.9. So what we need is to have the final value of output equals 0. We know that the disturbance is applied, but if we have a proper controller, in this case we don't have any controller, the controller is just a gain, and that gain is 1. But if we have a proper controller, we can reject the disturbance effect. So in this case, disturbance is 1 over S, and we don't have the pool of disturbance in the controller as it was in the theorem. So if I have the same example, but this time the controller is, for example, 1 over S. So if I do that, you can do it yourself in MATLAB or Simony and see actually what I write here is true, because here I'm just writing according to the theorem, but you can do simulations and confirm that. So if disturbance is 1 over S, but this time we have the unstable pole of the controller here, of the disturbance here in the controller, and because of that, if I do the same simulation, which means that I apply a disturbance, so the disturbance jumps, but basically this jump of the disturbance, because it is a step, this time is 0. So that time was also 0. So it jumps at t equals 0. What we have for the output, y of t, you can actually simulate that as well. The output goes all up, but it comes back to 0, which means that YSS, the steady state value of YSS, is 0. And because reference is 0 and YSS is 0, therefore the steady state error is 0. That's why I wrote in the theorem that steady state error is 0 if you have the unstable pole of the disturbance here. But anyway, the result is that, the conclusion is that you should always have the unstable pole of the disturbance in the controller in order to have the steady state effect of disturbance on output equal to 0. Okay, this example actually shows exactly what I mean. Maybe the last example I have for this section. I have, it's a bit more advanced example. We have a system which is 1 over S multiply S plus 1, or maybe S plus 2. I have what I have, I know that the reference is step and also the disturbance is a step. The goal is to have output equal to a step and also reject the effect of disturbance on the permanent output. Okay, the goal is the same as what the goal is all control loops, which means that output should follow the reference and reject the disturbance effect. So if I want to talk about the controller, what should we design for the controller here? Because if we only focus on the reference has one unstable pole, and the unstable pole should be here in order to have the steady state error equals 0. So which means that in the forward pass we should have S equals 0, which already we have. So because already we have S equals 0, even if I write 1 here, which means that a simple controller, then if there wasn't any disturbance, then this simple controller was enough for the system, because we have this pole, unstable pole in the forward pass. But the point is that we also have a disturbance equal step. Because of that, the controller, just to reject the disturbance effect on the permanent output, then we should have S here. This S is needed here, not because of the reference, because of the disturbance, to reject the disturbance. But having the S here, you could see that actually it makes the type of system equal 2, because we have 2. Reference was 1 over S, was a step. It wasn't necessary, but we added that because of the disturbance. But if I write 1 here, what you should be careful is that the control loop is not stable in this format. I remember I gave you the same example. I also didn't prove that the loop is not stable, but the example we had that here at page 4, that we had the same example, and also I wrote that the closed loop is not stable. So if I write 1 here, right now we have the pole here and the steady state value of output is okay. It doesn't have any effect from this disturbance. But the point is that if you add S here, then the loop is unstable. You should add something here in the numerator to make the loop stable. Right now, at the moment, you don't have the knowledge how to add a 0. I will tell you that S plus 1 is good enough to make the loop stable. But later you will see that how I have found this S plus 1. It's not, by the way, the only term you can use, but it's one of the solutions you can use. So it could be also S plus 0.5, S plus 1.5. It doesn't have to be 1. But there should be a 0 here just to make sure the loop is stable. So remember, when you design the controller, and when you are fulfilling the conditions to have a steady state error equals 0, to reject the disturbance, and because of that you add some integrators, because this one is an integrator. You add some integrators in the forward path. Make sure that these integrators, in general, having an integrator in the forward pass or adding integrator in the forward pass makes the loop less stable. So stability is not just on and off, even though we can define it as a system is stable or not. But because we are talking about the poles of the closed loop system, and if the poles of the closed loop system are far from the imaginary axis, we can say that system is more stable. It means that it is far from instability. So when you add one integrator in the forward pass, actually it decreases the stability margin. So always be careful about that. So in this case, we should add the 1 0 here just to make sure the system is stable as well. So in this case, if you design this controller, it's enough to follow the reference and also to reject the disturbance effect. So that was, as I said, that was an example. So at this point, the discussion about the internal model principle, disturbance effect, how to reject the disturbance effect is completed. And we are ready to talk about the controller, how to design controllers.